So if we start looking at problems for section 8.5, once again doing hypothesis testing on standard deviations and variances, we're going to start off by taking a look at number 4. Okay, so on number 4, it refers back to number 1 where we talk about in waiting lines, the Jefferson Valley Bank once had separated customer waiting lines at each teller. Now they have a single feed as they're going through, and they gave us some data results from this as we look at it. So it says for the sample data from exercise 1, we have a standard deviation equal to 0.5, and we want to use that sample to test the claim that the sample is from a population with a standard deviation less than 1.8 minutes, okay, as it was in the past with multiple waiting lines. So we want to basically, the claim is that we're less than 1.8. Once again, this is minutes in here. So if we look at our null hypothesis, so once again, part A asks us for our null hypothesis. So our null hypothesis, once again, is going to be equal to, so sigma is equal to our time in reference, 1.8. Our alternative hypothesis now, because our claim is less than 1.8, it does not include this, so our alternative hypothesis will be our alternative hypothesis here in this. So our claim is with this as we look at this, and once again we have minutes within. Part B asks us to calculate out our test statistic. Okay, so if we calculate out our test statistic, once again we're talking about sigma, so our standard deviation. So we're going to use our chi-squared. So chi-squared equals our n minus 1. So if we go back, they had n equal to 10. So our degrees of freedom is 9 times our standard deviation squared divided by our population standard deviation, or basically our variance divided by our population variance, which is 1.8 squared. If we calculate this out, we get 0.694. Once again, it tells us to round to 3 decimal places. On part C, it asks us to use the TI-8384 plus calculator to calculate this out. We don't have that option, so we're going to skip part C. Now, if we consider what is happening a little more in depth into what we're discussing here, let's look at part D for this, okay? So on part D, they talk about that the p-value is 0.0001, okay? So if we were to consider this p-value right here was given to us, we would then have to reject the null hypothesis. So we're going to reject the null hypothesis. Once again, this p-value is extremely low. Common one is our 0.05 is what we generally test towards. So because we would reject our null hypothesis, means that we are showing support of our claim because we're showing signs that the alternative is, and once again that's where our claim is. So now we would come in and we would state that there is sufficient evidence to support the claim that the standard deviation of all waiting lines is less than 1.8 minutes. Okay, so basically by us showing this, and once again they gave us this, in the next problems I'll show you how we'll actually compare our value in here to what's going on with our critical values of chi-squared. But because they gave us a p-value here, we could reject that null hypothesis. And then we're showing signs that, yeah, we're supporting the claim in this towards our test. Now, for part E talks about basically the practicality of this. So it says, what does the conclusion suggest about the effectiveness of changing from multiple weighting lines to a single weighting line? So because we're showing that our variance is less than what it used to be, we're showing that the change, so the change to a single line is effective because customers have a smaller variation of waiting times. So basically what we're saying here is that when we had people where they would come in and they would go into, let's say, 3 different lines right here. Oh, this line keeps moving, this one keeps moving, this one keeps moving, and these people just sit here and wait. Now by putting them all in the same line, the first one goes, they're gone, then as a teller opens up, the next one goes, then as another teller up, the next one goes. They're all getting serviced faster and at a more equal pace. So we're showing a better effectiveness to this. If we move on to question number 8. Okay, so on question number 8, here they talk about the preceding exercise involved the claim that post-1983 pennies have weights with a standard deviation less than 0.0230 grams. Data set 21 in Appendix B includes the weights of a simple random sample of 35 pre-1983 pennies, and the sample has a standard deviation of 0.03910 grams. We're going to use a significance level of 0.05 to test the claim that pre-1983 pennies have weights with a standard deviation greater than 0.0230 grams. Does it appear that the weights of the pre-1983 pennies vary more than those of post-1983 pennies? So basically in 1983, they changed that manufacturing process overall by distributing maybe a different combination of copper in there, different sizing, different weights, thickness on there. So they change it in somehow or some form, and now we're going to test that, hey, what's really going on? So once again, we want a significance level of 0.05. We look at our null hypothesis, okay? So on our null hypothesis in this part, we're testing the standard deviation. Once again, that post here would be 0.0230. So we have our sigma is 0.0230 grams. Our alternative hypothesis, so we're testing, or the claim is that the pre-1983 pennies have weights with a standard deviation greater than 0.0230. So because it's not equal to this, so our alternative hypothesis would have to be our claim then. Now, given this information, we are going to want to calculate out our test statistic. Okay, so we want to calculate out our test statistic. So I'm just going to go down here, our test statistic. Once again, is going to be chi-squared for this situation. So we're looking at this, and we see that, if I come up here, our sample came from 35 pennies. Once again, with a sample standard deviation of 0.03910 grams. So if we think about our test statistic, once again, is our degrees of freedom, or 39 minus 1, so we have 34, times our sample standard deviation squared, or basically our sample variance, divided by the population variance, or the sample variance, which once again we're relating to our sigma right here, which we're claiming that it is equal to 0.0230 squared here. If we calculate this out, we get 98.26 for our consideration. Sorry, can't read my own handwriting. 48.26. Let me take that back once again. It is 98.26. Now, if we're considering that we have a significance level of 0.05, I'm going to bring in my table in here. A little blurry, but overall I just kind of want you to kind of see where I'm going with this. Do realize that we want to be greater than. Okay, so once again, because this is greater than right here, we're talking about a right tail test on here. So that means we want the area to the right to be 0.05 for our significance. So if we come in here, if I hold this up a little bit, we see that we have a left side graph. Once again, this is our left tail because we're talking about our significance levels, our degrees of freedom in here with significance to be 0.995, 0.9. 0.95 would mean that it's a 0.05 significance to the left of this. So we're going to come over here and we're actually going to go down on this column right here where it says 0.05 to the right. So we're going to follow this column down. Okay. Once again, we're going to follow it down till we find our degrees of freedom, which is 34. Okay. So our degrees of freedom was 34. And we see that in our table we have 30 and then 40. We don't have a precise one here. But if we follow that over and we look at 0.05 for where 30 is at, so if we have 0.05 where 30 is at, we see that this gives us 43.773, and then 40 for 0.05 gives us 55.758. Okay, so if we notice we have these two values, so if I were just to kind of come here and quick draw what's happening, once again, the chi-square test is that right tail, that right skew right on here. So as we consider the values, we're just going to kind of draw these two values in here, that 43 and that 55. Once again, the decimals in here. Anything to the right of this would be critical then. If we notice, 98.26 is way over here. So we're showing that, hey, this value for chi-squared is in our critical area. So that means that we must reject our null hypothesis. Okay, so we come back here and we state reject the null hypothesis. Okay, now that we rejected the null hypothesis, we look back to the claim, and the claim is stating that pre-1983 pennies have weights with standard deviation greater than this. So because we rejected where it's equal to, we're showing signs here. This is our claim, so we can support our claim now, because once again we rejected the equality of this. So now we come and state that there is sufficient evidence to support our claim that pre-1983 pennies have a standard deviation greater than 0.0230 grams. And then it kind of gives us a follow-up question. It says, does it appear that the weights here vary more than those? So the weights of pre-1983 pennies appear to vary more than post. So, okay, so we're seeing that pre-1983 pennies appear to have a larger varying weight than post 1983 pennies. And that's kind of what our claim is testing towards. If we look at our next problem, once again, we'll look at problem number 12. Okay, so on problem number 12, here again, once another penny problem. Standard deviation for population, once again, isn't the biggest concern for most places, but does tell us very specific things within. So we always want to analyze what it is. So once again, analyzing of pennies. So an analysis investigation of the usefulness of pennies. The cents proportions of 100 randomly selected credit card charges from the author are recorded. And if they have a mean of 47.6 cents and a standard deviation of 33.5 cents. If the amounts of 0 cents to 99 cents are equally likely, the mean is expected to be 49.5 cents, and the population standard deviation is expected to be 28.866 cents, using a 0.01 significance level. Oh, sorry, hit my camera here. So once again, our significance level is going to be 0.01. To test the claim, okay, so I'll write my claim up here this time. So my claim here is that the sample is from a population with a standard deviation equal to. So basically our population standard deviation equals 28.866 cents. If the amounts of 0 cents to 90 cents are equally likely, is a requirement of a normal distribution satisfied. So if we consider right here on what is going on, we have to discuss, is a normal distribution really done, or are each of these equally likely? Okay, so if we were to consider that, let me come in with a different color here, that 0 to 99 cents in a transaction is equally likely. This is talking about a uniform distribution. Okay, so if we remember back, our overall claim when we test our chi-squared, our standard deviation on here, we have to fit a strict normal distribution. Okay, so it has to be strict. Now, this is not a normal distribution. Okay, so what's ever going on here, results are questionable. Okay, that we can perform the test if we don't meet any guidelines for anything, and it happens all the time in real life. People put out test values, test things that aren't necessarily true, but they look like they could be, but because of some other requirements that we're missing, they're actually a little more misleading. I mean, look at all our current issues with our virus that's going around, and people state this, and then they talk about different things. Basically, they're performing tests that should be performed. Here we're actually going to do one just so you can see what the values would be, but overall this test is, the results are going to be questionable. They could work or they couldn't work. We don't know for sure. Once again, sometimes you can finagle things to get it to work, but it shouldn't be done. This is going to be one of those times. So if we consider what's going on, we're going to state our null hypothesis. Okay, so our null hypothesis, once again, is the equality on this. So 28.866 cents. So we're testing our claim is our null hypothesis. So do realize that in our statement afterwards, whatever's going on, we will not be supporting this claim. We'll either be rejecting it or not rejecting it, okay? Basically that we will either show signs that, hey, it's not true, or we'll show signs that it's not true. Once again, that whole double negative type stuff that we can't support it because it is part of our null hypothesis. So that means our alternative hypothesis, because this is the claim, is going to be everything outside of that claim. So it is a do not equal, okay, or a not equal to. So now we have a two-tail test that we're referencing in here. Okay, so what this means is we're going to have to break apart our significance because it's two-tail. We're going to have to break the significance up into two different parts. Okay, so we have to divide it by 2. So we're going to have to look at a right part and a left part on this for any values. Once again, we could either find values that would be below or above. So as we kind of go through here, if I look at my skewed graph on this, we would see that we'd be testing here, and here would be our critical values that we'd be referencing towards. So our test statistic could come from over here, or it could be over here. Once again, if this value we find is less than, or if that value we find is greater than. So what we do is we start performing our tests. So we'll take our chi-squared value. So we'll have our chi-squared to find our test statistic. Once again, we look at what was presented. We have 100 different outcomes. Okay, so n equals 100. Because this 100 different outcomes is in here, that means our degrees of freedom is 99. If degrees of freedom is 99, we will come and look at our sample standard deviation. So we go back to the problem, and we see that our sample standard deviation is 33.5. So we'll square that. And then we'll divide it by our population standard deviation, which once again comes from right up here, so that 28.866 squared right here. In calculating this out, this is going to equal 133.337. Now what we have to do is we have to figure out, well, what are our critical values? So once again, we had 133.337. We're looking at critical values. Once again, degrees of freedom would be 99. So if we kind of come in here, once again noticing on top of here, we're going to be using the 0.995 because that would tell us 0.005 to the left of this. And then we're going to use the 0.005 right here because once again that's going to be to the right of this. So if I come down, I see that 100 is my only option down here. So I see 100 is 67.328. And then we also see on the very right-hand side, we have 140.169. So as we're looking at this, we're seeing, let me just bring this over and in here, with our critical values, basically 67 and then 140. Now do realize this was for degrees of freedom equal to 100. Our degrees of freedom is 99, So if I come back up here, our degrees of freedom equals 99. So it's just something to be careful of, that because we don't have the technology that we need at this point for this test, we're going to have to try to figure out some assumptions on here. So if we look at our value that we had is 133 point here. So if I come right here, here's 133. Considering everything that's happening on this, if I were to take degrees of freedom back to 90, that would mean this one right here, that would be 128. Okay, so 128 would be roughly right on here. If I look at this, 99 is really close to 100, so I'm pretty sure that we have a situation here where this null hypothesis is really having some issues. So because it's over here, we will state fail to reject the null hypothesis. Okay, so we're going to fail to reject this null hypothesis. Because this is, the null hypothesis was part of our claim, now what we'll state is that there is evidence. Notice I did not use the word sufficient evidence here. Once again, because of how I had to test this, I couldn't precisely define that this was in here. So I'm not going to say sufficient because we are fairly close within our values. So there's just evidence. Okay. Okay, once again, there is not evidence to reject the claim that the standard deviation is 28.866 cents. Okay, so once again, there is not evidence to reject this claim. So basically, we're never going to side with the null hypothesis. So when we fail to reject it, that means that we're not going to side with this. Because our claim is our null hypothesis, we can't say, oh yeah, we're supporting this, because this null hypothesis was an assumption to be true. That's why we will never support this. We can support not it, which would be that alternative. So here, basically, we will either not have evidence to reject the claim or have evidence to reject the claim. Okay, in this case, because we failed to reject it, we don't have enough evidence to reject that, hey, this could be happening. But once again, do realize that because our test results when we're working in here was talking 0 to 99 cents is equally likely, that's a uniform distribution. So even though we're showing that, hey, yeah, this is possibly working, our test isn't valid. Okay, so we don't have validity. Okay, so I'm just going to put in here on here so you can see this, not valid. Okay, well, once again, we could definitely question it because we're violating some principles on here for the test. Once again, not ethics into this. This is just our testing procedures. But so you can see what goes into a two-tailed test. This is an excellent example of what we need to see just in case it does come about.